Hi guys, uh, we continue the Gauss elimination method. Let's take an example to see what kind of problems we might be facing. If we take this example where the first equation in the system is epsilon x1 plus x2 equals to 1, and the second equation is x1 plus x2 equals to 2. This is a system where we can know for sure that 1 1 is an approximation of the solution because 1 1 satisfies the second equation and almost satisfies the first equation because epsilon is very small. So if we try to solve this equation with a Gauss elimination method, but for the first trial we consider that equation 1 is the pivot equation. So we keep the equation 1 and then we try to put to 0 the coefficient of x1 in the second equation. So uh, we multiply the first equation by 1 over epsilon, and then we we calculate 2 minus 1, equation 2 minus equation 1. We will have this kind of solution. Okay, so it's 2 minus 1 over epsilon over 1 minus 1 over epsilon for x2 and 1 minus x2 over epsilon for x1. So if this is epsilon here, if epsilon is very small, 1 over epsilon becomes very large, which means that the numerator in here will become close to 1 over epsilon or minus 1 over epsilon, and the denominator as well will be close to minus 1 over epsilon. Then x2 will be close to 1. Okay, if x2 is close to 1, then x1 is close to 0, which is not the solution that I was hoping to get, which is 1 1. Now, if I do the other trial, considering that equation 2 is the pivot equation, everything will change because I will have 1 minus epsilon x2 equal 1 minus 2 epsilon. And now if epsilon is small, then x2 will be almost equal to 1, which will lead to x1 equals to 1 as well. So the choice of the pivot equation is crucial. It will uh, it might lead me to a wrong solution or might take me to the good one. We'll analyze a bit what we should do to overcome this difficulty, but let me just point out that it's very important that when you do numerical analysis, we follow each step of the calculation to know that if we have a very small number somewhere in our calculation, this small number, will it lead to a very large number? Are we dividing by this very small number? Or it will lead to something multiplied by this small number, which will go to 0 and not affect our calculation. This is a very important thing that we should follow throughout our calculations to be sure that we are not exaggerating, we are not amplifying a tiny number that we would not like to amplify. So to overcome this difficulty, we go to the partial elimination method with pivoting. And when I say with pivoting, it means that I will switch the equations so I don't have a pivot equation that will amplify the errors. And to do that, we should not have a pivot equation where the pivot is equal to 0 or very close to 0. In other words, it should not be a pivot which is very, very small with respect to the other pivots. Okay, so if I look at the pivots, I should choose some pivot that is in the range of the other pivots and not something very, very small with respect to them. So in the first method of the Gauss elimination with pivoting, I will put a criteria that I will follow to choose my pivot equation. Okay, and you know that if you exchange the equations and if you put them in another order, the solution will not be affected. I mean, the system ax equal b will still have the same theoretical solution x. Okay, so what we do is that we will choose the pivot as being the maximum between the other pivots in absolute value. So if your pivot, or if you look at all the pivots, you will choose the one which has the highest absolute value. And if you choose this one, you will consider that this is the first equation and you will act accordingly. First, I mean the pivot equation. First, in the first step, And in the second step as well, I will look to all the equations and I will see if I have a pivot which is larger than the pivot that I'm currently considering, I will exchange the equations accordingly. Let me point out something more, that if you want to do so, you will not really exchange the equation in the matrix. I mean, you will not exchange the rows in the matrix. So what I will do is that I will put my matrix, okay, as it is, the augmented one, of course, and then I will put next to it an index vector which goes from 0 or 1. I can start by 1, so first equation, second equation, third and fourth. Now let's consider that the pivot equation that I want to be the pivot equation is the third one. Okay, so this is the third equation. Instead of going and exchanging the matrix and putting the equation in here, and then equation 1 in here, 2 in here, and 4 in here, instead of doing so, because this is a time-consuming thing when you are programming a large matrix. You know, if you have this matrix and the first one here, and you want to exchange row 3 with row 1 on the computer, how would you do? How would you do it? If you put all the elements in 3 instead of 1, you will lose all the variables in the row 1. So you have to put all the variables in row 1 in another column somewhere, then put all the variables in row 3 instead of 1, then taking back the variables that you stored in another variable to put them back in row 3. This is the very standard procedure. Of course, we have some special algorithms to make things a bit easier when you want to exchange, but it will be still a long procedure if you have a lot of variables. So what we can do is that instead of doing so, we will put the same matrix as before. We will keep line 1 at the position 1, or row 1 at the position 1, row 2 at the position 2, row 3 at the position 3, row 4 at the position 4. But in the index vector, in the vector of indices that I have created, 1, 2, 3, 4, I will exchange the rows. I will put 3, 2, 1, 4. So where I have 1 in my index vector, I will consider that this is row 1, and I will act accordingly. So I will be putting to 0 these variables in here, and this will be in here the pivot that I will be considering. Okay, so I will not exchange physically the rows, but I will exchange them in the way I'm doing my calculations. Okay, I will I will go to another partial elimination method where I will make an example so you can understand how this index vector works. So in the second method, instead of choosing the largest pivot as the pivot equation to indicate the pivot equation, I will choose the normalized largest pivot. When I say normalized, it means that I will take the pivot I want to consider and I will divide it by the largest element on its row, and this will be somehow the indicator. And then I will do the same in the second row, the third row, and the fourth row. And when I do so, I will look to the highest value of these ratios, and the highest value will indicate the pivot equation. Don't worry about what you are seeing here as notations in VI and everywhere, okay? Because these are only notations, and what I need you to understand is the technique that you will discover right now with me in the example. Don't worry. Okay, so the difference between the first method and the second method is only how to choose the pivot. In the first one, I choose the pivot as being the largest element between all the pivots, or the candidates to be pivots. And in the second one, I will choose the pivot as being the pivot equation is the one that will give me the highest ratio of the pivot that I wanted to be pivot divided by the largest element on its row. So technically, I will choose SI as being the largest element on each row, S1 the largest element on row 1, etc. And I will calculate at each step the AIK K over SIK, so it means that I will divide the pivot by the highest element. Let's see on the example how it works, and then you will understand everything. So this is the matrix A in the system, AX equals to B, and this is B. Okay, so I start by saying this. Then I will put first the index vector on the left side. So I will give an index to each row. This is row 1, this is row 2, this is row 3, this is row 4. And then I will put in here the scale, what I call the scale. What's the scale? It's the highest, the largest element in the matrix, okay? Of course, I don't look at the B, because what I'm doing is that I'm trying to perform the Gauss method on the matrix, not on the B. The B is only being modified according to my calculations. So the scale is the largest element in absolute value on the matrix A at each row. So 13 is the highest element at row 1, 18 at row 2, etc. Then I will start by pointing out the candidates to be pivots. So I have 3, minus 6, 6, and 12. Let's calculate the ratios. We have 3 over 13, the first ratio, 6 over 18, the second ratio, 6 over 6, which is 1, the third ratio, and 12 over 12, 1, the fourth ratio. So the highest ratio in here is 1. Okay, I can take this one or the second one, but I'm taking the third one. The highest ratio is 1. So my pivot equation will be the equation number 3. So I will keep the matrix as it is, but I will exchange my index vector, and I will exchange 1 by 3 and 3 by 1. So my index vector will be like this. Now I will start perform my calculations. 6 will be the pivot, okay, and I will start working as if this row was the first row, and I'm doing the echelon form, the standard echelon form. As we agreed before, I put here the coefficients. So 12 minus 6, the coefficient is 2. I put 2 in here. I make the difference and the calculation, and I have this new matrix after the first reduction. Okay. Now, for the second step of the reduction, my candidates to be pivots are the first row. It's done. We don't touch it anymore. My candidates now are 4, 2, and 12. The scale, I will keep it the same. I don't change the scale throughout the calculations. So I will calculate the new ratios. I have 12 over 13. I have 2 over 18 and 4 over 12. Okay, so the highest one is 12 over 13. That's why my new pivot equation will be equation number 3 in here. Okay, or the equation whose index is 3, which should have been in the third position if I were changing the order of the rows. Okay, physically I mean. So this is this should be the second equation. So now I will exchange the row 3 with the row 2. So I will exchange them in this vector in here and keep them in the matrix. So my pivot now is 12. It's in here. I don't touch it. And then I will put to 0 the element in here and the element in here. Okay, those elements should be echeloned to 0. So I do the calculation, I do the combination between the rows to obtain zeros, and I put in here my coefficients, and so on. I continue the same procedure. Now my pivots should be the candidates are 13 over 3 or minus 2 over 3. I divide them by 18 and 12 to find the highest and continue my calculation. So which will lead me to this triangular system. So this system is the following one: 6, minus 2, 2, 4. and then 0, minus 12, 8, 1, and then 0, 0, 13 over 3, and then minus 83 over 6. Finally 0, 0, 0, and minus 6 over 13, multiplied by x1, x2, x3, x4. This is 83 in here, and equals to, on the right hand side, we have minus 27, minus 45 over 2, 6, and 12. And then to solve the system, you will proceed as we discussed before. With the reverse path method, we calculate x4, and then x3, and then x2, and then x1, and we have the solution that is given in here. Okay, so this is the Gauss reduction method. Usually we should choose in the beginning which method we are using, whether it's the Gauss elimination method, the standard one, or the one with pivoting, with the standard pivoting, or the pivoting with normalized pivots. Now we will go to the part where we will now use these coefficients that I have been storing in my matrix, because until now I'm not using them. Now I will show you how to use them, or why they are interesting to be used.